So we can change the temperature of the Earth and the climate by changing the altitude of clouds, the coverage of clouds. We spoke about the cirrus and the low clouds. But there's another way we can also impact the climate, and that's by changing the number of these small cloud condensation nuclei, which the droplets form on them. As we mentioned, that every cloud droplet forms on some nuclei. These start as freshly nucleated particles, which may be a nanometer in size, which come from various sources, both the oceans, organic, ammonia, also pollution from humans, sometimes gas, particle conversion, chemistry reactions in the atmosphere form these very tiny nanometer particles, which can grow into more than 50 nanometers into what we call CCN, cloud condensation nuclei. Again, there are many natural sources, but also man-made sources of these. And eventually, when we also have saturation in the atmosphere, we'll grow droplets, which will get to more than 10 microns and eventually larger. But what happens if we add a lot of air pollution to the atmosphere, more and more of these particles in the atmosphere? So let's compare a clean environment, say over the oceans, compared with a polluted environment, say over an industrial area in the continents. What we see here is on the temperature or altitude on the y-axis, showing height going up in the atmosphere as the clouds grow. And we can see evolution as a function of time on the x-axis. Now, when we have a very clean environment, we have less particles. So there may be, for every centimeter cube, for every cc, maybe a few hundred of these particles where the droplets will form on them. So we have maybe a few hundred droplets per cc. In a polluted environment, it may be 1,000, 2,000 of these particles in the same volume. So what happens in a clean environment is that the drops start to grow, and there's less competition for the water in the cloud, so they actually grow quite quickly. If they get transported up, they'll freeze into ice, and because they're growing fairly quickly, especially in warm clouds, as we spoke about before, they'll fall fairly quickly as rain, and we can get rain developing within 20 minutes of these clouds forming, say, over the oceans in very clean environments. If we now add pollution and these particles, these aerosols, to the cloud, the same cloud even, what happens is we have many small droplets, because each droplet is forming on an aerosol, and there's competition from each one to get water to grow into a cloud droplet and eventually a rain droplet. And so the droplets are much, much smaller in the cloud. They take longer to grow to the size of rain to fall, and maybe they won't fall as rain. And therefore, the cloud will actually even last longer in time because we're not removing this water from the cloud, but we actually may not have rainfall from these clouds. But in addition, when we look at these clouds from above, we see we can actually change the color of the clouds and the brightness of these clouds by changing the amount of these particles. So on the left, you can see what it would look like if we zoom into these clouds in a clean environment. You see we have a lot less droplets, and the droplets are much bigger than in the polluted environment when we zoom in, which we have much smaller droplets and many more. Now, when you have many more smaller particles, you actually make the cloud much whiter than normally. And you can see in the background, in the clean environment, we may have maybe not a gray cloud, but a less bright cloud. On the right-hand side, when we add pollution and many more aerosols, all of a sudden we have a lot whiter clouds and brighter clouds, higher albedo, and according to the arrow, you can see we have a lot more reflection of solar radiation out to space, which would eventually cool the land underneath these clouds. Again, we can see here a normal cloud, which has maybe an albedo of maybe 70%. Some of the sunlight will travel through the cloud and go through. 70% is reflected. In a polluted environment, maybe 90% will get reflected and a lot less will go through the clouds. So the smaller the average size of the droplets, the more reflection of the sunlight and the whiter the clouds. Well, an example of where this happens in nature is what we call ship tracks. This is an image from a satellite over the Pacific, west of the United States, I think. And what you see, these lines, these white lines, these are clouds. It's not the smoke from the ships. These are clouds which have changed their color. They become much brighter because these are the tracks that ships have gone, and the exhaust coming out of the chimney of the ship has put many more particles into the atmosphere. If you look carefully around these white lines, there are clouds. There are clouds all over the place, but the clouds which are influenced by the ships have actually become brighter because we have now many more particles, many more droplets, and they're much smaller than the regular droplets. The smaller the droplets, the more scattering of sunlight, the more reflection of sunlight, and the whiter these clouds become. Another example here, we can zoom into that image, and on the top again we can see the ship tracks, these white lines. At the bottom we can see some satellite estimates of the size of the droplets in these clouds, and you can see that the lighter the color, the smaller the droplets. This is going from 6 microns to 30 microns. So the darker purple colors are droplets which are 30 microns in size. The light yellow are down to 6 microns. And again, the average size of the droplets are getting smaller. And in the top picture, you can see this makes them brighter in color, reflect more sunlight, a higher albedo, and in the long term would actually have a cooling on the surface because less sunlight is making it to the surface. Now, some people think maybe we can use this to our benefit in what people call geoengineering, and we'll talk about this maybe later in the course. Geoengineering is artificially trying to engineer the climate to prevent global warming, to offset global warming. Maybe artificially we can use this knowledge to whiten clouds, to make the clouds on the planet brighter, to increase the albedo of the planet, to reflect more sunlight, and to cool us down, and to offset the changes in the greenhouse gases. And some people have proposed having ships which run maybe on solar energy, which will travel around the oceans, will pump up sea spray from the ocean into the atmosphere. As the sea spray evaporates, it produces little particles of salt. These salt particles can go into clouds and increase the number of droplets, reduce their size, and brighten the clouds. If we can do this artificially on a global scale, we can maybe cool the climate, reduce the temperatures, maybe not have to worry about climate change anymore. Well, we'll talk about this later, but often when you do these quick fixes to the climate, in some other place in the world, you see some side effects like changes in rainfall patterns. So you may affect the temperature in one place, but it may affect circulation, rainfall in some other place. And so you need to really study this carefully before you use this in reality. Another thing, what happens when we add more of these CCN, these cloud condensation nuclei, is that you can, as I mentioned, delay the process of producing rainfall. In the natural atmosphere, on the bottom part of this plot, again, we have few particles, so we have few droplets, and therefore they can grow fairly quickly by taking up water vapor when the air is saturated, fall as rain, as warm rain, but also if there's ice in the cloud, the ice can take and grow fairly quickly into snowflakes, ice crystals, and fall fairly quickly as precipitation. If we add many aerosols, CCN, into the atmosphere, again, it's competition between each droplet. They're much smaller. The ice crystals are much smaller, much more difficult for them to fall to the ground. And so we can actually reduce the rainfall, extend the lifetime of the clouds. But for people who rely on the rainfall for irrigation of their crops, having longer lifetime, less rainfall is a big problem. There are also other cloud aerosol effects, and this is also an area of a huge amount of research, ongoing research, because the interaction between aerosols, clouds, and climate is very complex and can both benefit but also harm certain parts, whether it's precipitation or temperature. And here are just a few other connections between, say, the less reflective clouds or the clean environment. The clean cloud would be slightly darker than the polluted cloud on the right-hand side. So we can see here that in the clean cloud, we have both the droplets, ice forming, rain will form fairly soon. These clouds are a little bit darker, so there's less reflection, there's less absorption by particles in the cloud. More light goes through these clouds, more transmission. But again, the large cloud droplets and the ice will reduce the albedo. But there'll be more precipitation, and the clouds will last for less time. So when you integrate it over the planet, there'll be less cloud cover on the planet. If we go to the right-hand side, the polluted clouds, then again we're having more particles, smaller particles. we have more reflection. Often in polluted environments, you can also have black carbon, these little black stars here, which can actually absorb sunlight and actually warm up the cloud. Less transmission of the light going through. So basically, we have an enhanced albedo. So on the one hand, you can actually cool the climate, but you can also have a longer lifetime of the cloud, which is not so good for people who want to have rainfall from these clouds. And the absorption by this black carbon can also sometimes heat up the cloud and cause them to evaporate. So as you see, many different possible directions that clouds can change as a result of climate change. Previously saw changing the altitude, but here by changing the particle size, the number of particles, you can have many impacts on the clouds, both positive and negative.